Welcome back. This is tutorial 6A, question 0B, and now we do subpart B. And we are here now to answer the question, by inspection of the sinusoid representation, directly find the DTFS coefficients. It means that we are not using the analysis equation, we are using the inspection of the sinusoid representation. Let's see how we can do that. This is Y. Y has three parts. One, the DC term, let's call this Y1n. The second term, Y2n, which is a complex exponential with omega equals to 0.15 pi and phase shift pi over 3. And the last term is a sine term. This is Y3n. The frequency is 0.3 pi. In the last example, we have found that n equals to 40 is the common period for all these three terms, and therefore yn is equals to y of n plus 40 for all n. Once we have found the fundamental period, therefore for DTFS, then what we are going to do is that we are going to have omega naught, which is the fundamental frequency of the Fourier basis, to have frequency 2 pi over n. That means 2 pi over 40. That means pi over 20. Once we have that, then we now can express all of these terms with respect to harmonics of omega naught. Now let's begin with 2. 2 is a constant, therefore it is on the zero harmonic of omega naught. So this is the answer. For constant 2, the k index is equals to 0 since we are using the zero harmonic. C0 then would be 2, the amplitude here with phase 0, because we are going to multiply 2 with phase 0 by a bunch of 1s. Remember, B0 is nothing but a vector of 1. How many of them? In this example, there will be actually R40. Actually, I should write C40 representing as complex number, but J is 0. That's the reason. So B0 is all ones, 40 of them. Multiplying by 2 angle 0 will give you 2 for 40 samples. Now, what about Y2 of n? Y2 of n simply is this coefficient minus 1 with pi 3. There's an error here, 1 angle pi 3. Okay, exactly. This is minus 1 pi 3, which is equals to 1 pi over 3 plus pi, or if you prefer 1 pi over 3 minus pi. So we did this. We convert this plus pi over 3 to be minus pi, and therefore now we have minus 2 pi over 3. So this is actually correct. So let me repeat. Why did we have this additional minus pi? Is due to this minus 1 term. We don't like the minus 1 term to be the magnitude, because magnitudes are only positive numbers. So we have to convert this minus 1 to positive number, and to do that we are introducing a phase shift of minus pi. And therefore now is pi over 3 minus pi, which comes out to be minus 2 pi over 3. So the magnitude is 1 and the phase shift is minus 2 pi over 3 for k equals to 3. Why is it k equals to 3? It's because we are interested in 0.15 pi for omega, and this is the same as 3 omega naught, because 3 times, what is omega naught again? Omega naught is 2 pi divided by 40, which is 6 pi divided by 40, which is 0.15 pi. So now you understand that k equals to 3. This is the k. K is 3 times the fundamental frequency 2 pi over capital M. For the third term, we have a 3 times sine of this. As a trick, we want to convert the sine into cosine first. You realize that it is easier to convert it into cosine, because then we would have 2 complex exponential that does not divide by the j term. So to convert a sine to a cosine, what we then do is we not only change this, but we must introduce a phase shift of minus pi over 2. Now, what we then do is that we will bunch this minus pi over 4 and minus pi over 2 together to get minus 3 pi over 4. We then break the cosine into 2 complex exponential. We convert this 3 cosine, this whole term, and it will become the complex exponential sum of 2 complex exponential of the same term divided by 2. So you realize that this part becomes a positive frequency because it's ej 0.3 pi n, and this one is a negative frequency e minus j 0.3 pi n. The phase shift is minus 3 pi over 4 here for this frequency, but because of these 2 minus become positive 3 pi over 4 here. Now, where is this? Where is 0.3 pi? It is at k equals to 6, because k equals to 6 implying 6, because why? 6 omega naught is equals to 6 times 2 pi divided by 40. What is this equals to? Is 12 pi over 40. This is equals to 0.3 pi. Now, what about the negative minus 0.3 pi? Of course, you can think of it as k equals to minus 6. But alternatively, k equals to minus 6 is the same because it is 40 samples periodic. K equals to minus 6 is actually minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. So it is at k equals to 34. How do I know this? K equals to 0 is the same as k equals to 40. K equals to 1 is the same as k equals to 41. So k equals to minus 1 is 39, and hence at k equals to minus 6 is 40 minus 6, which is 34. So this is how we see that when we plot only for positive k's, then we are plotting this complex exponential here at k equals to 6 and at k equals to 34 for k equals to minus 6. So these 2 complex exponential is for these 3 cosine. Now, it's 3 divided by 2, so the amplitude is 1.5. The phase is here. This figure shows the phase. This phase is minus is 3 pi over 4 is plus 3 pi over 4. And here is minus 3 pi over 4. So you can see the values here. So with that, now I hope you understand that we have just simply solved the problem of converting this equation without doing any DTFS, simply by converting them into complex exponential and identifying the respective k's along this axis and the amplitude as well as the phase, and plotting the DTFS coefficients. Thank you.